ft, then I'm going to use impulse train separated at delta t. Then what I will do, I will multiply this ft with impulse train. So now you know that what will happen here in this region. In this region, it is function. This impulse train is zero. In this region, impulse train is zero. In this region, impulse train is zero. So whatever the value of the function in this region, whatever the value of the function in this region, if you can see in between between these two, whatever the value is between these two, whatever the in this region, whatever the value is, it is going to get multiplied with zero. So whatever it doesn't matter. Whatever the value was, it doesn't matter, right? So that will become zero because I am multiplying my function with my impulse train. So the value at this point will matter because it is multiplying with some non-zero entity. Value at this point will matter because it is multiplying with some non-zero entity, and here it is multiplying with zero, and hence whatever the value is, it is suppressed. So at least I got these points. How I obtained it? I multiplied my function with my impulse train. I multiplied my function with my impulse train, right? And you know that if I am integrating, you know that function is multiplied with impulse, and if it is integrated from minus infinite to plus infinite, it is going to result into function at the point where impulse exists. So now if I am integrating this function from minus infinite to plus infinite, if I am integrating it from my function from minus infinite to plus infinite, what I am going to get is the function at the points where impulse exists. I'm going to, if I, so what I will get here, I will get my function at the point where this impulse exists. This is a function of a function where this impulse exists. I think you can, this is shifting property again, because you can see that impulse train is nothing but multiple impulses. So whatever the shifting property was one impulse, now it is applicable for all the impulses, right? So actually instead of okay, so now let us see. Let us conclude the things. This is my function. This is my impulse train. Can you see this impulse train? This impulse located at n delta t. N will vary from minus infinite to plus infinite. So if n is zero, it is delta. It is at zero. Then n is one. Then it is at delta t. N is minus one. Then it is at minus delta t. So on. So this is impulse train that we have already studied, right? And now what I'm doing, I'm multiplying this two. I'm multiplying this two. Ft actually. So what I'm doing is actually I'm multiplying with ft with, if I'm doing this multiplying with impulse train. So impulse train is like summation of delta. I hope you can understand. I'm not writing everything. So actually ft multiplied with summation of delta. But I can see the same thing as, I can take ft inside summation, inside of the summation. Why? Because ft is not varying with respect to n. So I can easily take it inside the ft. Ft I can take inside the summation, and I can write the equation like this. So if I am multiplying my function with impulse train, it will look like this. Any doubt in this? Right? So what exactly it is? It is function multiplied with impulse, integrated here. It is not integration because it is a discrete domain. It is not a continuous domain. So you can consider it is like integration only. It is summation because it is a discrete domain. Right? So integrated from minus infinite to plus infinite will result into what? The function where impulse exists. Here impulse exists at all n delta t. I hope it makes sense to you, and this is how we can obtain a sampled function multiplied with impulse. This is sampled function f tilde. F tilde is known as a sampled function. Okay, fine. So what actually we did, we multiplied function, and so now how you can see a sampled version? You can see sampled version as a continuous function multiplied with impulse train, right? So multiplication of two different function and impulse train. Now actually I was not interested at all in the function. What is sampled version? I know I can see my sampled version in time domain easily. Where I am interested in, what happens if I find frequency domain of my sampled version? I know that whenever I will do any operation, on image is actually my sampled version. It is not my continuous version. It is my sampled version. So whenever I will find Fourier transform of in my image, actually I am finding what Fourier transform of a sampled version. So where I am interested in Fourier transform of my sampled function. what exactly happens if I am finding Fourier transform of a sampled function. So Fourier transform of this is nothing but Fourier transform of this multiplication, because both functions are equal, right? And you know that Fourier transform of the multiplication results into convolution in the frequency domain. You know that that convolution theorem, what it says? Multiplication, Fourier transform of a multiplication results into convolution in the frequency domain. So actually I wanted to find out Fourier transform of sampled function. That means I wanted to find out Fourier transform of this multiplication, but I know that multiplication results into convolution in the frequency domain, and frequency domain of this is f of mu. And suppose it is f of mu, f of t has its Fourier transform f of mu. Impulse train has its Fourier transform S of mu. If you remember, we have already found Fourier transform of impulse train in the previous lectures. We have already found Fourier transform of impulse train. What was that? This is what the convolution theorem I was talking about. Multiplication in time domain, convolution in frequency domain. Convolution of what? Frequency domain or representation of both. Right? So now what is frequency domain representation of my function? I am assuming it is f of mu. What is frequency domain representation of my impulse train? That already I have found earlier. So this is what Fourier transform of the periodic impulse train that we already found, and it is this one. Just remember, it is what, 1 by delta t, and impulse train at n divided by delta t. It is my Fourier transform of a impulse train is 1 by delta t and summation of delta at n by delta t. Just remember it. This already we have found earlier. Now, so this is what we already found. 1 by delta t, delta at n by delta t, summation of it, that is impulse train. Fourier transform is this, already we have found in the previous lecture. And okay, now what is the definition of convolution? If so, now what I want to find out, okay, I know what is Fourier transform of my sampled version. It is nothing but convolution of Fourier transform of my original continuous function and my impulse train. That is what I concluded till time. But actually, I want to find out this in detail. So what is my next step to do? Okay, let's find convolution here so that we can get idea of what exactly is going on, right? So I want to find out convolution here. So convolution of f of mu with this function. Now, what is the definition of convolution? Definition of convolution is, if I want to find out convolution of ft with ht, then I should flip this function. I should flip this function, and I should multiply it with the original function, and I should shift by the same amount that I have here. Right? I should shift by the same amount that I have here. Okay. And integration should be done from minus infinite to plus infinite. Okay. Now, so if I want to find out Fourier convolution of this, what, just use the same definition, but just find convolution of this. Or how to find? So I will need one dummy variable first of all, from minus infinite to plus infinite. I will need one dummy variable d tau. Here, as I needed the tau, again I am using the tau variable only. Here t was not used here. T was not used here. Same way mu will not be used here. On dummy variable, the same variable I am using tau. You can use any dummy variable here. What to do? So take another second function that I am taking, second function s, flip it. So I am flipping it with tau, shift it, flip, shift, multiply, integrate. So I have flipped it, shift by t. What is t? T is the variable here. What is in my case? What is in my case? What should be my equation here? It should be like this. My whatever the variable I have, that variable I should keep here. I want to find f of mu converse with s of mu, so I should shift it by mu. Earlier I wanted to find f of t converse with h of t, that's why I shifted with t. And then my first function, capital F, and the variable will be tau. Variable is this is dummy variable. It is not like time domain or something like that, right? It is just a dummy variable. This is actually in frequency domain only. We are capital F and capital S are frequency domain representation only. Okay. So any doubt regarding to this definition? So actually, this is nothing but this. Okay. Now substitute the values. So what I have S of mu, but what I need is S of mu minus tau. How to get that S of mu minus tau? If I have S of mu, but I want to find out S of mu minus tau, how to obtain it? So wherever mu is, I should replace it mu minus tau. So I will get S of mu minus tau. So wherever mu is, I will replace it mu minus tau, mu minus tau. So what I am having here is um, that f of, so what exactly I have here is f of tau delta, if you can see, delta mu minus f of tau summation delta mu minus tau minus n by delta t d tau. Any doubt up to this step? This is what the Fourier transform of my sampled version. This is what my Fourier transform of my sampled version. So if I have a continuous scene, if I sample it and if I find its Fourier transform, actually up to this I will reach. Any doubt up to this? Anyone? Anything should be repeated here? Okay, so I'm assuming that all of you are following. If not, then please ask, because highly important values, highly important equations and conclusions we are going to derive. Anyone having any doubt, please ask. Okay, so assuming all of you are comfortable with it. Now, so now what is the next step? You can alter the sign of, you can alter the order of integration and summation. So we have altered that order. We have altered the order, and now this is what I have. Just this f of tau function integrated from minus infinite to infinite d tau. So what exactly it is? It is actually function multiplied with impulse integrated from minus infinite to plus infinite, and this is how I can use shifting property here. What shifting property says? My function, this integration will result into the function where impulse exists. Where this impulse exists? Where this impulse exists? This impulse exists at little thing that no, Mayank, think more. What is the variable first? Tell me. Yes, Priyal, it is true. Mayank, what is the variable here? Our variable is not mu minus tau. Our variable is tau only. Why? Because I am integrating with respect to tau only. So how to obtain? Equate the argument with 0 and obtain the value of variable. Right? So value of variable is the tau will be mu minus n by delta t. Right? So here I think all of you must be clear with, see how we obtain. Suppose it is delta, say x minus 5, where it exists, that x minus 5 exists at, if I equate this equation with 0, whatever value of my variable x I obtain, at that location it exists. Right? So here also, if I will equate this with 0, whatever value of my variable I will get, at that location it will exist. The variable is tau. Why variable is tau? Because I am integrating with respect to tau. So variable is tau, so it will exist at tau is equal to mu minus n by delta t, and hence my function value, the impulse will exist at mu minus n delta t, and hence the shifting property says the result will be f by the result will say that the result will be the function at mu minus n delta t, the function at mu minus n delta t. Okay, and n is from minus infinite to plus infinite. Okay. Now what was, see exactly what, observe what exactly you obtained. It is very interesting and unique result we have obtained. So any doubt up to this? Now we will understand. This was mathematics, right? Now we have to understand the meaning of it. We have to understand the meaning of that we are going to. But any doubt in this, that the mathematical formulation? Okay, so now fine. This is very much important result. So now recall what we have studied till time. I had my function f of t. This is my f of t, which was a continuous one, right? What was its for frequency domain representation? This frequency domain representation was f mu. F mu is what? If I consider f mu, not f bar, you should not consider this line. If I consider f mu, that was frequency domain representation of my continuous function, which was f mu, right? Then what I did, actually I sampled it. So I obtained like this, something like this. I have sampled it and I obtained some samples. Now what was my interest? I wanted to know what will, so if I what I obtained f tilt of t. Why? Because I cannot store the continuous one. And what was my interest? My interest was to know that what exactly happens in frequency domain of my sampled version. So if I find frequency domain of my sampled version, what I obtain in my frequency domain, that is what my requirement was. I am assuming that f of mu was looking like this. Suppose this is a triangle shape and it was having this triangle shape. I'm just assuming that this function was having this frequency domain. That is possible. Now, if I sample it, what happens to my frequency domain? So that's why I obtained this equation. What this f of mu means? F of mu means my original frequency domain transform. Suppose it was centered at 0 and it was having some triangle. Can you think what exactly I obtained here? Can you draw this? Can you think, or can you imagine this? What exactly is this? What is f of mu minus 1 delta t? If I write n value is 1, so what will be this? Suppose n value is 0, n value can be from minus infinite to plus infinite. Suppose n value is 0, what exactly it will be? If n value is 0, this will result into f of mu itself. So my frequency domain of my sampled version will have my original function f of mu, which is centered at 0. Assume my n value is infinite. Right now my n can take from minus infinite to plus infinite values, right? Right now assuming n is having value 0. Suppose n is having value 0, the summation will vanish, right? Summation is n is having 0, right now n is having 0 value. And this is 0. That's why this will be f of mu multiplied with 1 by delta t. Suppose amplitude was 1 here. Suppose the amplitude was 1 here. Now what will be the amplitude? Can anyone tell me what will be the amplitude now? If this was 1 amplitude, now what will be the amplitude? For n value 0, what will be the amplitude? How to obtain amplitude? Suppose yes, it will be 1 by delta t. It will be 1 by delta t, true. So amplitude will be 1 by delta t because it is 1 by delta t into f of mu. So definitely amplitude is now multiplied with 1 by delta t. So this amplitude, if it was 1, now it is 1 by delta t. It is scaled by 1 by delta t. Amplitude is scaled by 1 by delta t. Okay, fine. Now, so that is n for n is equal to 0. But my n can take any value. Suppose n is taking value 1. Then what will happen if n is taking value 1? Think where it will exist. For n value 1, where f of mu will exist. What will be this term? F of mu minus 1 by delta t. This term will be f of mu minus 1 by delta t. Where it will exist? Minus, will it get shifted by left side or right side? It is f of mu minus 1 delta t. It will get shifted by right side, on the right side by value. It will be centered now at, it will be centered at, yes, it will be centered at 1 by delta t. Yes, it will be centered at 1 by delta t. And the amplitude will be 1 by delta t. I hope you can understand the amplitude is also 1 by delta t. Okay. Same way for n value 2, can you tell me what will happen? For n value 2, what will happen? Where it is centered? Yes, sequence of same function will be there at 1 by delta t, then 1 by 2 delta t. On the right, for negative values of n, what will happen? For negative values of n, what will happen? This will be 1 by 2 delta t, and this is 1 by delta t. For negative values of n, it will get shifted on the left hand side by 1 by delta t, then by 1 by 2 delta t, and then what is the requirement? For all these n values, I have to do summation. So if you will observe, the wherever this function exists, this function is 0, all the functions are 0. So summation will be like, it will look like the existing triangles at this is how the summation will look like, because whenever this exists, all other functions are 0. So summation of this with zeros. Whenever this exists, all other functions are 0. Whenever this exists, all other functions are 0. So how exactly it will look like? It will look like my f of mu is shifted to locations 0, 1 by delta t, 2 by delta t, 3 by delta t, so on. Right? So this is what I am going to obtain. This is what I will obtain. You can see, this is what we are obtaining. Our repeated version, repeated f of mu at 0, 1 by delta t, 2 by delta t, and so on. Okay. Now, suppose I say this is mu max. This is, say, I say mu max. And this is minus mu max on this side. Just keep that in your mind. We will need it, and I will give you the understanding of the same. So what exactly we obtained, that if this was my Fourier transform of my continuous function, now if I will sample my function and if I will find its Fourier transform, then I am going to have this as my Fourier transform. So my whatever my Fourier transform earlier was, it is repeated at 1 by delta t, 2 by delta t, so on. From what is delta t here? What is delta t here? Delta t, if you observe, delta t is nothing but the gap between two samples. The gap between two samples. That is how delta t came. Okay, these things are useful. We will keep it in our mind. Suppose I am taking delta t larger. Suppose I am taking delta t larger. What will happen? Suppose I am taking delta t larger, 1 by delta t. What will be the value of 1 by delta t? Delta t is larger. 1 by delta t will be smaller. Yes, it will be smaller. That means earlier what was the case? Yes, 1 by delta t will be smaller, and what actually I have to do? How to obtain how to obtain frequency domain of sample function? Frequency domain of the sample function is my original frequency domain shifted at 1 by delta t, right? And if delta t is smaller, it will get shifted nearby, because 1 by delta t is smaller value. It will not be far from 0. It will be somewhere here. So if I keep decreasing 1 by delta t, can I say this is decreased 1 by delta t? This can be one of the scenario possible, because I have to shift at 0, then 1 by delta t. But now 1 by delta t is having smaller value. That means the distance from 0 will be smaller, and hence these triangles are touching each other. Right? Now suppose I further reduce 1 by delta t. That means I further increase delta t. What will happen? What will happen if I further reduce delta t? I am further reducing, further increasing delta t. I am further reducing 1 by delta t. What will happen? My what I want is, if, this should get repeated at 1 by delta t, but 1 by delta t is not this far now. It is even smaller. So somewhere here it will be. So now this is my function. It will get repeated here. At this, it will be get repeated. So it will look like this. My delta t is smaller now than the previous case. 1 by delta t is smaller now than the previous case. Right? So now what will happen if I'm reducing 1 by delta t further? What I'm getting is, I'm getting such overlapping. Right? So that overlapping, this overlapping will result into a straight line, because see, if you will see, wherever this function exists, this function is very less. Wherever this function is decreasing, this function is increasing. So summation is constant. Both are having equal value. Here the second function is increasing, but first function is decreasing. So again value is constant. Here also second function is higher, first function is zero. So value will summation of these two will remain constant. So how you will look see the shape? You will see the shape like this. You will see the shape like this. Actually, it occurred because of overlapping here. Okay, so what we observed that if I am increasing delta t, if I am increasing delta t, 1 by delta t becomes smaller, and hence these triangles are coming near to each other. Triangles are coming near to each other, and there is a one scenario possible that my 1 by delta t is such a small value, that delta t value is such a high value, such so that my two triangles are overlapping with each other, and the final shape is looking something different. Actually it should look like this, and it is looking like this. So my final shape is looking somewhat different. Okay, so someone may say, okay, but how does that matter to us? Though it is looking like this or this, how does that matter to us? Okay, so now one question to you. Suppose okay, so now I had a continuous function here. Then I had the sample version, so it was looking like this, right? Or this, or this. That depends on my delta t value. These three, all three are the versions that depending on 1 by delta t. This is how my sample version frequency domain will look like, right? So suppose now I want to obtain my, I want to go revert back. If I want to see, okay. What is this? What is his question? Let us learn. What I am talking about is, see, this is how my triangle. This is another triangle. This is my first triangle. Okay. So now, whenever this is non-zero, what is the value here? Okay, this is higher. Like whatever the value. Suppose this is value is higher. This is non-zero. What is the value here? It is almost zero, right? So summation is this value plus this. Right? Now, I am taking sample somewhere here, I am taking value here, right? The slope of this line and slope of this line is same because it is the same function, right? The amount by which this is decreased, the same amount this is increased. So what will be the summation now? The amount here is decreased, the sum amount here will increase, and hence the value will become a straight, yes, I think it's clear to you, that's good, fine. So it will be a flat line, a straight line, because the slope of both lines are same. Now, um, what was our point? The point was, okay. So I hope you will understand this point now. Um, Now suppose I have sample version, right? But actually I know if I am doing sampling, I am losing the information. So that is not preferable. That is my, I don't have another scope. That's why I'm going for the sampling. Otherwise, who will not like to have a continuous C, right? As you know, in the butterfly image or in that line image, if you see, if I was having sample version, definitely there was loss of information. But I had the limitation. That's why I have to go with, I have to tolerate with the sampled version. I have to deal with it. But okay, but in case if I'm able to get my original version back from my sampled version, it will be beneficial to me anyway. Okay, so if this is my sampled version, if I want to go back here, is it possible to go back from this version to this version? Is it possible? What actually I wanted this. Actually, what I wanted this. I wanted my function should be continuous and hence its frequency domain should look like this. But because of limitation, I had to sample it. I had to deal with the sample version. If I sampled, I obtained actually this. What I wanted this one. I wanted this, but what I obtained is this. Right? So, is there any way to go back from this to this? So someone will say yes, you can go back. How? If I am suppressing all these triangles in the frequency domain, if I am suppressing all these triangles in my frequency domain, okay, and so if I am suppressing, how to suppress these triangles? So simple thing is that if I want to suppress all these triangles, if I want to suppress all these triangles, then I should use a low pass filter. I should use a filter. What is filter? Filter will pass some frequency. It will suppress some other frequencies. Those are filters. Filters. So I will use a filter which will pass. These are frequencies only. No other frequencies. I will use a filter which will pass only these frequencies. It will suppress all other frequencies. So this is actually low pass. Why? Because it is suppressing higher values of mu. Here also negative, but values are higher. Negative, these are negative mu values, but um, negative mu values are there, but they are, see, can frequency be negative? What is frequency? Frequency is number of cycles in my sinusoidal. Or we can say in one, frequencies cannot be negative, right? So what is the significance of negative mu values here? That if you remember for the frequency, if I have a sinusoidal of, not less frequencies, no, not like that. If you remember scalar representation of any sinusoidal, we represented it with a circle with radius 1, if you remember, and then we had that if it is having angle omega t, or it is having, yes, it is sine omega t. If it is having angle omega t, then it can be represented like this, where this is omega t. This is omega t. This was a scale. This was a vector representation of your sinusoidal. We have already studied this, right? So what was, so then if omega, if your t changes, then actually you were moving towards in this direction. If t changes, then omega t was changing, and hence your values were varying like this, and hence you were obtaining this type of shape, oscillating, or this particular shape. If you remember, this we have studied in our 12th mathematics. What is that? This angle is omega t. T should vary. Here also t varies. If t varies, the amplitude changes. Amplitude changes the range from 1 to -1. So this was level 1 and -1. Earlier this amplitude was this. Now amplitude is changed here. Amplitude is changed here, and it will become 1. Then it will again decrease, 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 and it will go like that. So this is how. This is what the representation of your sinusoidal was, right? And this was omega t, and it was varying in this direction. Suppose I am, instead of taking omega t, if I am taking minus omega, then minus omega t means what? If your t changes, it is going to vary like this. It is going to vary like this. Your vector will rotate in anti-clockwise direction instead of, or rather in clockwise direction instead of anti-clockwise direction, right? So that is what, yes, it will vary in clockwise direction. So that is what the significance of negative frequency is. Actually, it is the same frequency as your positive frequency, just the scalar rotation, or rather vector rotation, is in the opposite direction than the another sign frequency. So here we should not get confused with negative frequency values. These are also the same frequency. Here just variation in your vector is in the clockwise direction. So these all frequencies are higher frequencies. These all frequencies are very high frequencies compared to these frequencies, and these are also negative values, but values are high. Suppose this is -5, this is the -2. Minus will not make any sense. Actually, we can say it is 2 in anti-clockwise direction, 5 in anti-clockwise direction, right? Clockwise or anti-clockwise, that depends, right? That depends on the sign, right? So actually, these values are higher only. So what exactly I am doing is, if I am passing this function from the low pass filter, that means I am suppressing high frequencies. If I am suppressing the high frequencies, then I can get my original function back. Though my amplitude will be 1 by delta t, but you know amplification can help in increasing the amplitudes. So amplitude is lesser, that's all right. Amplitude will make, just reduce the amplitude of my time domain. That's all right. I will amplify, but I will get my original signal shape back, right? So so it is very easy to obtain my function from. It is very easy to obtain my function, original function, from this. Can I obtain the same? Can I obtain the same from this? Can I obtain, if I am sampling at this rate, if I am if I have sampled with delta t value such that, if I have sampled my delta t value such that delta t is higher, my delta t is higher, and hence 1 by delta t is smaller in such a manner that these triangles are just touching each other. Can I get my original function back by passing it through low pass filter? If this is the scenario, can I get my original function back from my by passing this from the low pass filter? Are you getting it? Are you clear with low pass filter concept? If not, I can repeat it. It's highly important because we have to use it in the image context. Should I repeat anything here? Okay, repeat from what point? Are you clear with low pass filter will help? Low pass filter is not clear with you? Okay, what is low pass filter? Low pass filter, what low pass suggests? What low pass suggests? Which frequencies are passed? High frequencies or low frequencies? Low pass filter will pass which frequencies? High frequencies or low frequencies? Tell me. Yes, it will pass the low frequencies. Low pass means it is going to pass the low frequencies. That means what will it will do with the high frequencies? It is going to suppress the high frequencies. It is going to reject the high frequencies. That is what the filter is. Filter is used for rejecting something and passing something, right? So what we are passing here, we are passing low frequency values and we are suppressing high frequency values. What are the high frequency values here? So I am adjusting. So I have not just, I have to decide, I have to give the threshold that value beyond this will be called as high frequency, value beyond this, below this will be called as low frequency. Suppose I am giving that threshold here. That value beyond this will be considered as high frequency and suppress them. Suppress them means what? All the value, function value for those frequencies should be 0. We should not have any value for those frequencies. That is how the frequencies are suppressed. And so same value will come here because see, if I am considering this as frequency, the same negative value, the frequency is same, just rotation direction is different, right? So what I am considering is all the values beyond this is considered as high frequencies, and lesser than that values will be considered as lesser than those values will be considered as low values, right? See here again I am repeating. Here negative sign is not mathematical negative sign. Frequencies cannot be negative. I cannot have negative cycles per unit time. Understood? Here what is the significance of that negative? Negative indicates that that vector in my unit circle representation will rotate in another direction. Otherwise frequency value is same as my positive values. So negative is not having the mathematical lesser and greater meaning here. Right? Suppose I am having -5, and if I am having -5, and if I am having -2, these two are the frequencies, then -2 is smaller than -5. The reason is minus is not having mathematical meaning here. What it indicates, this function is having frequency 5 and rotating in my the values are rotating in the, I mean values are opting by rotating my scalar rotating my vector in the anticlockwise direction. Right? Same way for 2. That I will obtain so so frequencies are 5 and 2 only, right? So 5 is always higher here than 2. So here if I consider these values are higher than 2, higher than these values here. Now can anyone tell me which frequency is higher here, -5 or +5? -5 or +5, which frequency is higher here? Yes, both are same. Actually, both frequencies are same. The frequencies are same. Actually, they are same frequency signal, and -5 and if 2 I am considering, then this is higher frequency than this. This is higher than this. Here both are equal. Understood? So I hope you can understand that. So now what I want is I want to pass these frequencies. I want to pass these frequencies. I want to suppress this. So how it will look like? So I want to pass these frequencies as it is. whatever the value is for these frequencies from 0 to whatever these values are, I want to pass it as it is, and all other values beyond this should be 0. How it will look like? It will look like this. It will look like this. Observe, it is looking like this. So actually I wanted this, but I could not obtain this, and I have to obtain this because of my limitation. But if I obtain this and then if I pass through low pass filter, if I pass through a low pass filter, if I am suppressing high frequencies and if I am passing the low frequencies, then I can go back here. So by limit, I just overcame my limitation. What I wanted a continuous function, and hence what I wanted, if I find Fourier transform of that, I should obtain this. But because of limitation of my device, I have to obtain this. I have to take samples. I cannot have this continuous domain. And hence, if I found Fourier transform of that I have got this. But actually, I didn't want that. Actually, I wanted this. So what I tried, if I am getting this, do I have any way to go back to my wanted, or I can reach to my requirement? So luckily I found, yes, there is a way to go back to my original required one if I am passing it through low pass filter, right? So for this it was possible to go back to this domain because this was my required one. Understood? Okay. Now, Jaimin, is it clear to you, or should I take another example and explain? Some other way I should explain? Okay, good. Now, can anyone tell me that will I be able to go back to my original domain or original continuous form from this? Suppose, yes, it will be possible to go back because I will be able to pass through low pass filter. Yes, we will be able to go back using this, right? And what about this? Will I be able to get my original function back from this version? If I will pass it through low pass filter, what I'm going to get is, if what I will get it, I will get like this. This will be the shape that I will obtain, and what actually I wanted the shape like this, triangle kind of shape. This information I am losing here. Mind explain what is the meaning of predictable here, or what you want to tell? What kind of prediction you want to discuss here? Till time what we can conclude is, okay, so what we can conclude is, if I am having delta t smaller, this was smaller delta t. Suppose I am taking case 1, case 2 and case 3. In which case delta t is smallest? In which case 1, 2, 3 delta t is smallest? In case 1 the delta t is smallest, right? True. So if I'm in case 2, okay, fine. Now what is the issue that we have to realize? Okay, what is delta t? Let's go to that point. What is delta t? Delta t is separation here, separation between two samples. What our result says, suppose I have a function, suppose I have a function suppose I have a function like this, then I should take a sample here, and the gap between two samples should be smaller. The gap between two samples should be, this delta t should be smaller. If delta t is smaller, then I'm going to have this type of cases, right? If delta t is larger, largest delta t is here, and hence I will not be able to recover my signal anyway. This is known as signal recovery. I will not be able to recover my signal in any way because I am losing this information here if my delta t is larger, right? So what is the significance of that? The significance of that is, this gap between two samples should be smaller, right? If I am having this type of sampling, then it is better, that is good, right? If I'm having this type of sampling, that is good. By delta t, you can see this much is delta t, right? Another way is, suppose I'm increasing, or if suppose I'm reducing delta t further, because I know that I want delta t smaller, as small as possible. Suppose I am reducing my delta t, it will be always better. See, you can see my delta t is smaller, and it is, I am getting by delta here. You can see my delta t is smaller. I am having more samples. I am getting more samples if my delta t is smaller. I am getting more samples, and of course, it is beneficial because I am able to get my signal shape. Yes, that is true, Mayank. If my delta t is smaller, that means I am taking more samples, and hence I am losing less information, and of course, it is better. That we know, if less information is lost, it is always better. Now assume that if my delta t is very large, what will happen? Suppose one delta t, I am assuming this is my one sample, delta t is larger, that means gap between two samples will be very large. So one sample I am taking here, another sample I will take somewhere, say I am taking somewhere here. Possible, this is my second sample. This is my first sample. So gap between two samples is larger. You can see very large, large gap is there. After that, I am taking. Then I am, suppose I am taking another sample somewhere here. This is my continuous function. You can assume that. So my delta t is larger. So next sample I am taking somewhere here. Then I am taking somewhere here, right? And so what I will feel is my function is varying like this. This is how I will feel if I'm taking that function. But actually my function was varying like this. Why that happened? I will feel my function is like this. If I'm taking this sample, then this sample, then this sample, because less samples, I'm not going to judge what is the shape of my actual function. I will not be able to judge from, if I'm having less samples, I'm losing a lot of information in between, and hence I will not be able to judge what was my actual function. I will not be able to get my actual function value. And hence it will not be able to recover, it will not be able to possible to go back to my original continuous function. If I am having more samples, it will be possible. Suppose if this is my function, if I am having more samples, if I am taking lot of samples, these are more samples and delta t value is smaller. Right? If I am having so many samples, can you judge what will be the shape of the function? What was the continuous function? Can you go back to continuous function? Yes, you can go back. You will understand. Okay, this is what my function was. You were able to go back to your original domain, original continuous function. But my delta t is larger here. My delta t is larger. So what I will, one function will be here. Next function will be here. Actually, the shape you can think it was like this. The shape of actual function was like this. But I have one value this, and then I have a negative value. Why would I think that my next function, my function was going like this? I will only think that my function is going like this. Then it is going like this. So actually, I will not be able to anywhere know that my function shape was like this. I will not be able to go back to my original function, which was not sampled. And that is what the concept of the sampling is. So here, so now tell me, in case of 1, 2, or 3, in which case more samples are taken? Case 1, case 2, or case 3, number of samples will be higher. In which case? 1, 2, or 3? Yes, in 1, number of samples will be higher, and that's why it is known as oversampling. More samples are taken, right? So this case 1, where delta t is sufficiently small, and hence more samples are taken, that is known as oversampling. While case 3 is having the less number of samples, or we can say least number of samples, and it is known as undersampling. And this is critical sample case. So now we have learned 3 sampling case. One is oversample, where delta t is smaller. Then the critical sample, and we will take more details of the critical sample in the next lecture. And this undersampling case. In undersampling case, it is not possible to go back to my original function or original domain. Original shape I will not be able to get back. And whatever information I am losing, that is known as aliasing. This phenomena is known as aliasing. Of course, more details on aliasing and critical samples we will take. But so what is our conclusion today? That I want delta t value smaller. That means I should lose less information, and I should I should be able to go back to my continuous story. That is what our conclusion for today. More details on this will be continued in the next lecture. Any doubts so far? Okay, fine. So we will take more details in the next lecture.
A very good morning to all. After this short, or you can say the long break, once again we are back with the sessions. And for the first of all, before starting today's discussion or today's session, we'll see some common mistake that students have done, many students have done in the examination. So we'll try to discuss that common mistake, and then later we'll start the new direction of our discussion, that is the unsupervised learning, and to be specific, the clustering algorithms. Fine. So the flow will be first the remaining flow of the syllabus. First, we'll try to cover this unsupervised learning, then we'll focus on the ensemble learning. And once we complete that remaining portion, then we have decided that this time we'll try to add some additional concepts like the neural network and if possible some deep learning concepts too, right? So now if we first discuss the paper, let me just share my screen. So we'll discuss only our portion, that is question 1 DEF and question 3. So one advantage that we have this time compared to the regular examination, or you can say the offline examination, is the length of paper, right? Previously we were supposed to restrict ourselves to 1 or 2 pages, right? So it was very difficult to give you the full algorithm and ask you something from the algorithm. So generally we are asking that how this algorithm behavior, what will be the behavior of this algorithm, and so on. But this time the good thing is there are no restriction related to the length. So what we thought, let's just give you the algorithm. I am talking about the question 1D, and let student identify what exactly the meaning of particular steps, right? So you have algorithm, so no need to mug up the algorithm. And I hope if you can recall the decision tree, at that time also we have discussed that do not mug up the algorithm, just try to understand. So the algorithm was given in the question paper, you just need to explain step number 8 and 9. But still many students are just what I can say, they just read the particular question, and from the question as well as from the algorithm, after reading, they are just writing some statement related to that step 8 and 9 without exploring or without giving a particular steps why it is needed and that all. And so if we just go to that algorithm, and if we just focus on step 8 and 9, so what we are doing from the attributes list, we are removing a particular attribute. So if you recall our the credit rating and so on. So from that, whichever attribute right now we have selected, and if you can recall that attribute is, we were referring that attribute as an splitting attribute. So from the remaining attribute list, we'll remove that splitting attribute, but not always. If it satisfies the step number 8, then we'll perform the step number 9. Right? So I hope first the step 9 is clear. In the step 9, we are just removing a particular attribute that we have selected right now. But when we'll perform the step 9, whenever the step 8 is true, and what we are saying in the step 8, splitting attribute is discrete value and multi-way split allowed. Right? And this comment might be helpful to you whenever you write the answer, not restricted to the binary tree. And so if these two conditions are satisfied, then we'll proceed with the step 9. Right? So that you are supposed to explore what is the discrete value and what do you mean by multi-way split. Right? And some of you have given very good example. Let's say many of you have, or not many, some of you have written that, let's say, the age criteria, and if I say that the age lesser than this threshold and higher than this threshold, that might be my splitting criteria. So in that scenario, the multi-way split is not possible, and so on. So many of you have explored this particular steps with the example. So that's really appreciable step. Right, and I hope that explanation covers the answer of 1 and 2 both. You need to explain this step as well as why it is not applicable to the binary tree. And for third question, many students have written the correct answer, and that is which algorithm? Right. But I have observed ID3 also in some paper. I don't know why particular student have written the ID3, but yes, it was there in some of the paper. I haven't gone through all the papers, but whichever paper I have found, majority of you have written that cart, but in many cases ID3 was also present. Right, so the correct answer for this should be the cart. Right, and in the given slide also it is mentioned that it is always restrict your answer to the binary tree, and thanks to cart always restrict your answer to the binary tree thanks to what? Thanks to the Gini index, right? Correct. Right. So that should be the answer for this question D. For E, simply you need to explain the softmax function, and I guess all of you have written it correctly, where you need to explain what exactly the softmax, how it control the probability values, and what should be the graph of the sigmoid function, that also you can mention. Right, so there is no need to discuss anything related to the E. But for the question 1F, very few students have written the correct answer, or I can say many students have not attended this question 1F. So if you just look at the question 1F, it is related to gradient descent converge. And you need to identify what is the difference when it converts in the case of convex graph and in the case of non-convex graph, or you can say in the case of convex and the non-convex loss function. Ultimately, we'll represent that loss function as a graph, right? So answer to this question belongs to the discussion of logistic regression, why we haven't choose the squared error function over there. Instead of that, we have defined some other loss function. At that time, we have discussed what will be the issue if we choose the squared error loss. Right. So if I just give you the straightforward answer, it should be whenever you use the gradient descent with a convex function, you can say whenever it converts, always it's a global minimum point. But this actuality you cannot provide with non-convex function. That means if you are using the gradient descent with the function which is not a convex function, in that case it might possible that whenever it converts, that point may be a local minimum. Right, so if you have written this answer, that's it. That's what we expect from this particular question 1F. Now for question 3, the first question where you just need to calculate precision and recall, but one additional point over here is instead of binary attribute, now we have instead of binary class, we have 3 classes, A, B, and C. This information assume that the feature set consists of following entries, then the total 800 students are just to divert your attention, because ultimately there is no role of this particular line in the answer. To write the answer of our question, you just need to focus on this table, and as it is mentioned over here, you have to round up the result after 5th plotting point. So for the first, the precision, the answer should be 0.49047. So if you just written 0.49, it's invalid answer. For the recall, I guess those who have attended, many of you are getting the correct answer, that is 0.5. But for the precision, you have to look at this particular instruction. Right? And one more thing which is mentioned over here is one versus all method and average of result. Right? So whenever we have discussed this multi-class related strategies, that is how can you handle the multi-class with the accuracy or the other measure. At that time we have discussed this. Right. And one thing is, I don't know whether you forgot this second question and you don't know what should be the answer of this second question, but many of you have attended the first question only, calculating the precision, the recall, and for the second question, many of you have left that second question and just consider the first one. How can we convert the above problem into the regression problem? Right. So the answer to this question is, over here we have the classes. That is, let's say if the grade range is between this to this, the grade is between this to this range, the grade value should be A. Sorry, the mark is between this to this value, the grade should be A. If it is between, let's say, 10 to 9, the grade should be A. If it is between 7 to 8 or 7 to 9, it should be B, and so on. So likewise, you have some range of marks, and based on that, you are predicting the grade, right? As it's a classification problem, right? But if you want to convert it into the regression problem, so instead of this grade, or you can say instead of this class A, B, and C, you need some value, the specific value for the result. Right? So simply instead of considering the grade, if I consider the marks, whatever is the marks value for the student, it works. Right? And we can convert this logistic regression, that is which is actually classification problem, into some regression problem, and you can solve it with, let's say, the linear regression. Fine. Now the second question, that is B, pure theoretical question, where you need to explain the logistic regression as well as pre and the post pruning, right? And this first answer, many of you have written the correct answer for this first, those who have attended, but for the second, pre-pruning, post-pruning, that's fine. Many of you have explained what is the difference between this pre-pruning and the post-pruning, but which are different techniques, what is the difference between the techniques, it's not found in many papers. Right, so you need to explain that techniques, at least if you do not we cannot expect that for 3 marks you should explain all the techniques in depth, but at least you should list the technique and maybe 1 or 2 lines related to the technique, what exactly happening inside that technique. And for this question 3a, this is the same example as we have discussed in lecture. Anyone have identified that it's in same example? Correct. So you all are the lucky guys, right? So it's in same example where instead of the okay, so if you have identified, can you tell me feature 1 and feature 2, which exactly the name of these features? What exactly the name of this feature 1 and feature 2? Correct. Right. So it's in same example. Only I have, instead of that string, I have changed it to the number, and also I have shuffled some rows values. That's it. Otherwise, instead of 4 features that we have discussed during the session, for ease of the calculation, I have provided only 2 features, feature 1 and 2. But the feature 1 is related to the income and the 2 is related to the age. And if your calculation is correct, you may get feature 2 is a root node. Right, and those who have attended this, almost many of you are able to at least identify that feature 2 is root node, no matter whether the calculation is correct or not. Right, but remember that the calculation also carries some marks. Right, so if you just identify that the feature 2 is the correct root node or the root label, that's not enough. You have to prove that with accurate calculation. Fine, but I guess it's very easy for those who have attended, and those who attended this particular question, out of them many are able to get the correct answer, right? Very few, maybe 2 or 3 might have written that feature 1 is the root node. Otherwise everybody have written that it's feature 2. For this question B, specifically if you observe the second scenario, it exactly represents the line. So if you just consider this 10, that is bias, plus w1 x1 plus w2 x2, you will get the exact y value, right, for any of the entry. And this instruction, that is ignored regulation and set alpha to 1, was missing in the original paper. Though I have provided that instruction lateral in the classroom, but it's fine if you miss this particular instruction and if you have chosen your own alpha value, and based on that if you perform the calculation, I have checked your paper accordingly, and whether if the particular calculation is correct, I am going to give you marks for that, right? So but for that you have to mention that this is the alpha value that you have chosen. Fine, it's fine if you haven't chosen the alpha is equals to 1 and if you have some different value, or maybe if you haven't chosen alpha is equals to 0.5 as per the given instruction in the classroom, that's fine, right? You can have any alpha value. Ultimately it's an hyperparameter, so it's fine if you choose the hyperparameter, but accordingly your answer should be correct. Fine. Any further doubt in the our in this particular question paper, or specifically our portion? Okay, so let's start the next topic now. That is clustering. So if you just go back to the first lecture, where in the introduction of machine learning, we have discussed that there are many categories. One can be a supervised, another can be unsupervised, then the reinforcement learning, and so on. So today we'll start the second part, that is unsupervised learning, or you can say unsupervised machine learning. And I hope you know what is the difference between supervised and unsupervised. In the case of supervised, during the training you have the class level. That means during the training you know exactly what is the answer. For example, if you consider, let's say, the image classification problem, where during the training, and let's consider the MNIST dataset that we have used in our laboratory too. So during the training, you know what exactly the correct class level of a given image, whether it's representing number 0 or 1 or 2 or any other number between 0 to 9. And so that was a scenario during the training. In the case of unsupervised, unsupervised machine learning model do not have any class label during the training process also. Right? You just have the data, but the data might have some common features or common similarity. So your role is to identify that similarity, and for that purpose there are many algorithms. One category is this clustering, where in the clustering we are grouping different items, or you can say different objects which belongs to your training or testing set. And there are many different memory clustering, but remember that when it comes to the clustering, that means it's similar to that we are talking about the unsupervised machine learning model, right? So the basic fundamental or basic idea of the clustering is we need the group that we have. For that example, there are no classes given. If cluster, we want to group them based on some similarity, based on some features. So how we'll do that? That we'll see in different algorithms. But right now, be clear with the aim. We want to create the clusters of a data, right? And there are many different parameters or the measure. It might possible that one single example may belongs to more than one cluster. So we'll see all that techniques one by one. But before that, we should try to be familiar with the terminologies which are used in this clustering algorithm. So if we begin with the discussion, so first thing, cluster. So cluster is just a collection of, you can say, data, or you can say collection of objects, or whichever examples that you have. From that example, you are supposed to create number of cluster or number of groups, such that for that particular group we need these two things. All the objects which belongs to a particular group are similar, or you can say are related to one another within the group, and it should be unrelated, or you can say it should be dissimilar to the other example which belongs to the other group. That means within the group we need the close connectivity, and if we have a separate group, we need a maximum difference or maximum distance between that separate group. That's the ideal aim of the clustering algorithm. If you are able to find any such clusters, that's the aim of any clustering algorithm, right? Somehow you have to decide that satisfy these two criteria. First, within the group, there should be a similarity, the maximum similarity, and if you consider different group, there should be a maximum difference between the different groups. There are many measures to calculate the similarity and that all. So we'll see that once we discuss particular algorithm, how we'll find the similarity. One can be the Euclidean distance that we know, right? But that is not the only measure. There are many other measures. So we'll see step by step. And so that's a basic aim. And as we know that it's a supervised learning algorithm where during the training also, you do not have any predefined classes. You just have examples, right? But from that example, you have to find some similarity between different, you can say, between different x values or between different samples. Right. And sometimes these unsupervised algorithms are also referred as learning by observations, while the supervised are referred as learning by examples, because you are giving examples to the supervised. I hope you are clear with the difference, because this is a very important difference between the supervised and the unsupervised model. And it always helps you to identify whenever you have a given data set, which kind of model you select. For example, let's say you have some data set, and if you try to plot that data set, if you try to visualize the data set, you may find there is a line. All the data belongs to a particular line. But you cannot use a linear regression or any classifier, or you can say any supervised model, unless and until if you have a class label for that. If it is a classification, if it is a regression, unless and until there is a specific value associated with every example, if you do not have that value, you cannot go for that. Either you have to generate that value for all the training example, or you have to retrieve that value from somewhere else, maybe from where you have collected this particular data. Then and then you can go for a supervised model. If you have the y values, while in a contrast, in the case of unsupervised model, don't worry about the y values. We do not need the y values. Whichever x values that we have, you can say whichever examples that we have, we'll try to find what is a common pattern in that example. And from that, we'll try to design different cluster and we'll try to analyze this cluster. So this all fundamental started with one very popular problem referred as the market basket analysis. I guess some of you might have heard about that market basket analysis. And if you haven't heard, I can assure that all of you might have observed that scenario with many malls. Let's say it's a case of DMart. Okay, voice is cracking. So let me just now. Okay, thanks. So what we are discussing the market basket analysis. So if you have visited any mall, or let's say if you visited the DMart, specifically let's consider the case of DMart. If you have visited the DMart, and if you just check the item which are present in different compartment, so can you find any similarity between the let's say for particular compartment? Can you find that there are some similarity over there, or within the particular section? Have you seen any similarity? If you have observed some similarity, you can just write it in a comment. Which kind of similarity you have observed? Similarity in terms of item, whichever items are present over there. So one observation I want to share with you, I hope from that you might able to identify many other similarities. Whenever you consider the kids section, or you can say kids clothing section, you might observe that always next to the kids clothing section, there is a section for kids toy. Where the first one, that is clothing, is you can say the necessity. So whenever you visit at that particular section, and what they have identified from the different buying pattern of a customer, if particular customer is buying some cloth for, let's say, his or her child, then there is very high probability that he or she will going to buy some toy. Yes, another example, Akshay, Maggie and ketchup together. Wherever you find the section of Maggie, you will always find a section of ketchup. Very might be next to that or very nearer to that Maggie. Right, so this is a kind of observation that they've made. So once we generate the bill, right? So once you buy some item and once you generate the bill, that is not just for the tax calculation purpose, or that is not just for giving you a you can say a hard copy of bill and to identify this is this much saving you have done. But based on the data that they have collected for different customer during different time period, they are making this kind of analysis. And that's why if you observed in many mall, frequently they are changing the counter of different items instead of keeping it a constant. By observing customers buying pattern, frequently they are changing the counter. Yes, that's also a good observation, Mayank. So it is to attract child or it is to attract the mother, child's mother. Female clothing section as well as you can say child clothing section are generally near to each other. And so there are different buying patterns that you might have already observed, right? But we might not aware about this algorithm, which is a very popular algorithm that is market basket analysis, and from that all this clustering and that all unsupervised learning is derived, where they are identifying the buying pattern of a particular customer. And whenever it's a particular customer, they are not focused on a single customer, but they will consider the data from all the customers as well as not from a one single store, from all the stores that they have. Yes, so now you guys are finding many different such scenario or many different patterns, right? So that's actually the association rule mining. So from this buying pattern, we are supposed to find some rule. And the rule means if I put these two items together, there is a very high probability that if customer is going to pick this item, he or she will consider this second item too. Right? So based on that, they have decided they might decide some rules, and based on that, they just put the items accordingly to increase their benefit, or you can say to increase the profit. Right? So for that, they do not have the label. The label means no customer will say that you are putting this value, this X item over here, put this Y item nearer to that so that I will always collect it together. But from analyzing different basket, or you can say from analyzing different customers buying habit, they are able to derive such kind of rule. So you can say they are able to derive such kind of frequent pattern, where these items, the frequent pattern means these items are frequently bought together. That means there should be some correlation between the two items. And they will also observe, let's say if I put these two items together, whether it increase the purchase of the two item or not. Based on that, let's say sometime it might happen that the rule that you have designed is not a proper rule, or it might not be followed always. There are many factors which affect this buying habit. One might be the environment. Okay, for the current scenario, that is this COVID duration, we may find this sanitizer bottles always available in the mall. So can you just imagine what should be the probable location of that sanitizer bottle? We know where exactly it is if you visited the mall during this particular COVID duration. But can you just think about the probable, or you can say the good point where you, if you put the this sanitizer bottle, there is a very high chance that it will be picked by a customer. Yes, yes, correct, correct, correct. So if at the entry level or if at the exit level, and exit level means definitely before the billing section, right? So if they have this sanitizer bottle very near to that, so there is a very high probability that customer will consider or customer will go for that. So once again, but let's say maybe after some time, whenever there is no COVID era, at that time, if they once again consider the sanitizer bottle, and if they put it at the same location, do you think that once again the customer will have the same buying habit? Not, right? The first thing is now there is a very less, or you can say there is no requirement of that particular bottle. Another thing is, uh, yes, that's it, right? That's the only thing. There is no requirement. So probably many customer will not go for that. So it affected by a particular environment too. So there are many measures. So always you cannot have a stick, or you can say you cannot have a static strategy that I will put this particular item always at this location. So this is a one example. Likewise, you can think many other example. I have written some examples in this particular slide where this unsupervised machine learning, or you can say unsupervised algorithms, comes into the picture, or you can say where this clustering comes into the picture. So if we think about some real world scenario, the first is, let's say, the information retrieval, where we need to cluster a particular document. Let's say you want to derive some knowledge related to this COVID. The knowledge means which are the recent research related to this COVID, then where it is initiated, what is the count per country, or you can say the per state, or whatever count you want, and so on. So you need the recent information, right? So you may have many documents present in the world, but from that you need a particular cluster, or you can say you need a particular group. So once again comes the clustering, where we are interested to retrieve some information. That information may be related to the COVID, right? But for that, we need only one single one cluster from all the documents which are present in the world. So in that cluster, I want the document in which there is some information related to this COVID. Next, land use. Right. So whenever you consider a particular, specifically for the civil engineers, whenever they consider a area, or let's say right now government has given the permission to build a 70 floored building in Gujarat, right? So whenever for that the land should be appropriate as per the requirement. I don't know which are the requirement with the civil engineers, but it should be such that it can able to handle, you can say, low resolution earthquake. And there might be many other factors which affect this land's capacity to handle that load. So for that, they can find the similarity between different lands which are present. So once again, there is no label. If you consider this example, there are no label. Nobody will tell you that these lands are similar. So you have to find some pattern. Maybe you may find some soil related testing of that particular land, and from that you may retrieve some pattern. Right. Yes. So that might be another scenario. Then marketing. So once again, this marketing is also a very important area where this clustering algorithm is right now used. Sorry for this interruption due to railway line which is very near to my marketing. So you might have observed this marketing scenario in the real world. Let's say if you consider any advertisement, digital advertisement, right? So let's say if you search something on the Amazon, you may find the advertisement related to that particular item. But that's fine. That's based on your search, right? So there is no relation of that answer with the clustering. But sometime if you observed carefully, you may find items that you haven't visited anytime in your, you can say, search history. You may not visit at that particular item, but still that items advertisement is there whenever you search something in the Google. So whenever you search something in the Google, So that is the scenario where once again this clustering comes into the picture. Because you have visited, let's say, some X item, but in the advertisement they are displaying you X as well as item Y. So how they decide that this Y item is very appropriate for this particular customer if he is looking for the item X? Let me give you an example. Let's say if you are searching for a new laptop, let's say if you are going to buying a new laptop, so you are searching for that new laptop maybe at Amazon, right? So if you observe carefully, you along with the laptop advertisement, or you can say along with the ad of your laptop, you may find many times you may find the offers on mouse as well as offers on headphone and offers on, you can say, the wireless keyboard and so on. So how they have identified these items are related. So if somebody is looking for the laptop, I should suggest him mouse, not a refrigerator, right? So that's an example, right? Refrigerator. So how they identify this thing? Once again, from the buying pattern, and they are using this buying pattern for the marketing. So these are some examples, or you can say these are some real world application where we have actually observed this clustering. We might not aware about that clustering, but we have actually observed this scenario, right? And so on. So if you observe some other example, one is the earthquake studies, climate related study, and the economic science, where once again the market research is there, right? So these are some application or the area where you can use the clustering, or you can say the unsupervised learning algorithms. Right. And that's not the only scenario. Clustering is not always used as the modeling, or you can say as is not always used as the final product to decide some output, or you can say to decide some rules. Many time it is used as a pre-processing task also. So I have listed few pre-processing tasks. So let's just go in the depth of all one by one. So the first is the summarization, where you can pre-process your data for regression classification, or you can say for the association analysis or association rule mining. How? So we know that whenever we have a data, and if the data is properly fitting, or you can say it approximately representing a line, we'll generally go for a linear regression. But what if we find some data, you have the label data, fine, you have a label data, but that data, if you just try to plot that data, they might represent two different lines, and both are almost separated from each other. And on that you want to perform some regression, and on that you want to predict something. So for such example, what you can do, you can find that cluster, you can say you can find that group. And for that, let's say in our example, we have found that there are two group. So for the two group, you can try linear regression, right? And to be, let's make it more complex. If you try to plot your data, and if you observe that some data point representing a line while other are representing some other curve, right? But they both sets are, you can say, separable. So once again, for the two examples, or you can say for the two data, you can have different algorithms. Maybe let's say for the one, you can just go for the linear regression, while for the other, you can go for some higher order regression algorithm, where it can represent some, instead of line, it can represent some parabola. Fine. So in such scenario, you can use this clustering is a pre-processing task before starting your original algorithm. Even though if you have the class label, or you can say even though if you have the regression answer, before giving that data directly to your original algorithm, if you come to know that from the visualization step, if you come to know that there are separate groups, so to identify such groups, you can go for this clustering algorithms. Or even to identify whether we have separate groups or not, you can go for this clustering algorithm. Next is, let's say, finding the k nearest neighbor, which means you can say the one application of this, you can say localizing your search on one, or you can say small number of clusters. If I try to give one example, let's say if you search news, maybe let's say in Google you are searching news, so you'll always get news related to the India prior to the news related to some other country. Let's say news related to the US, unless and until they are very important news. So the point is, because they not simply know that from your geographic location that you belong to the India, so it is better to serve you with the news which are related to the India rather than serving you with the news which are related to some other country and might not be of your interest or might not be that much important news. Right? So they are trying to find the cluster. This is a one criteria to find the cluster, right? Your geographic location. But there are many criteria. Another thing is to detect the outlier. Many times this strategy is referred as the anomaly detection algorithm or anomaly detection. So let's say the very popular problem of this is credit card for fraud. Your regular transactions, if you consider your credit card, let's say your regular transaction is between 100 rupees up to, let's say, 10,000 rupees per month. But assume that at particular month, your transaction value is, let's say, 10 lakh. So that is kind of outlier, or you can say that is kind of abnormal situation. So bank will verify whether that particular transaction is valid or not. So that is something which is referred as the outlier detection, or you can say outlier analysis. So you have some group, you can say in our transaction case, the group is the amount between 100 to 10,000, right? So that's, you can say, your group. Your group means the customer from for which we are exploring this example. So 100 to 10,000, that's a group, but certainly, or you can say for particular transaction, the value is very far from the current group. So that, you can say, might be a scenario of outlier, or you can say for this banking related transaction, there might be a possibility of a fraud transaction. So bank will verify that transaction, maybe by calling customer or maybe by some other way. Right, so that is referred as anomaly detection. You can say the outlier detection. So once again, the clustering algorithms can be used in such scenario. Right, so after discussing these different examples or different scenarios where you can use this clustering algorithm, let's just try to go in bit depth of what we expect from this clustering algorithm. So as we have discussed in the initial slide, we need two things: high intra-class similarity and low inter-class similarity. That means within the cluster, whichever examples that we have, there must be a very high similarity between them. And as I have discussed that which are that similarity measure, we haven't focused on that because they may vary from application to application. as well as there are many parameters to identify the similarity, right? But assume that for our algorithm, whichever parameter that we have identified, after the execution of my algorithm, what we want, whichever clusters that my algorithm has identified, the clusters are such that within the cluster, whichever examples are there, all should have a very high similarity, whichever measure that I have. That value should be high if I consider any two samples, or you can say any two example within the cluster. The similarity value that I have considered, that should be very high. But if I pick one example from one cluster, and if I pick one example from the other cluster, the similarity value, and later if I compute the similarity value between the two examples, it should be very low. So if my clustering algorithm is able to achieve this criteria, then you can say it's a good clustering algorithm. Right? And if you observed, we are just saying that high and the low value, high intra-class similarity and the low inter-class similarity. But we are not saying what exactly that high value and what exactly that low value. It varies from algorithm to algorithm, similarity measure to similarity measure, as well as it varies from data to data. Right? But that you can say a very ideal situation, you can say very important observation if you want to say whether the particular clustering algorithm is good or bad. Right, and the quality, how much good your clustering algorithm is decided based on the similarity measure which is used, its implementation, and this third point, which is a bit interesting, based on how many hidden pattern it is going to identify. Right. Once again, if we go back to our example of market basket analysis, so we have identified over that Mayank का कीधु तू? Let's say if we keep clothes of female as well as a kid together, then there is a very high probability that they will be picked. Both of that particular scene will be considered by a customer if any one of them is considered. So that is a one rule. Likewise, we need many rules, and that rules are actually referred as the hidden patterns. Pattern means, let's say if I put X and Y together, then there is a very high probability that I should put Z also over there so that X, Y, and Z will both come together. The other rule might be I should not put A and B together, never. If I put it together, customer will either pick A or B. And so on. So likewise, there might be many rules, or you can say there might be many hidden patterns, and you can say the algorithm better if it is able to identify some or all patterns. Again, how many patterns are there, that we don't know, right? Because ultimately it's once again an unsupervised model where this count is not known priorly. But yes, sometime if you observed this hidden pattern, you may find some surprising pattern. Right? So if you have a time, just whenever you have a time, just search it on a Google, this market basket analysis, and one surprising result whenever the algorithm discovery was started. They observed two items. There is no correlation between the two items, but they observed frequent two items both together. I guess it was in US and some other country, I don't know. But I can tell that it's not in India, but somewhere else they've done this survey, and they have identified that some item X and Y, if you buy it, the customer were frequently buying that particular two items together. And then they have analyzed that scenario, then they've analyzed the market, and lateral they have identified due to this rule, people are buying these two items together. And so if you have time, just go through that history from where this whole clustering as well as the market basket analysis and the priority algorithm comes into picture, right? And from that all this field comes into picture. Okay, so with this, I'm concluding this lecture. In the next lecture, we'll go into more technical depth of this clustering. Thank you.
So hello everyone, I hope I am audible. You have enjoyed the first internal paper of compiler construction, and today we'll continue with top-down parsing. In the previous session, we have gone through how to remove the useless variables, how to perform elimination of left recursion, left factoring, and all that issues. And also we have gone through using a predictive parsing table, how we can derive a given string using a top-down approach. So we'll start from the starting symbol of the grammar. Using the predictive parsing table, we will derive the required string. This is what we have seen in the previous session. So now in this session, what we'll do is we'll see that how to construct that predictive parsing table. So for that, we have to learn how to calculate the first set from the given grammar, how to calculate the follow set from the given grammar, and based on first and follow set information, we can construct predictive parsing table. So today, in this session, we'll learn how to construct a first set. So now, let us see that what is the first set. So basically, the first set is the first terminal symbol which we can derive from the given grammar production, or we can say the first terminal symbol we are getting from the given non-terminal during the derivation process. So now, to calculate a first of x, here x is a terminal or it can be a non-terminal. But for the x, if x is a terminal symbol, then first of x is equal to x. So for the terminal symbol, the first of x is itself. So basically for the terminal symbol, we don't have to do anything, in short, because the terminal symbol itself is the first of it. If x is a non-terminal, if there is a production rule, f produces null. If we are able to generate a null, basically we have a direct production. It is not indirect rule, it is a direct rule. If x produces null, then we'll add the null into first of x. Here x is a non-terminal. The third rule, which is the most crucial rule, is if x is a non-terminal and x having a production y1, y2 up to yk. So y1, y2, yk can be a combination of terminals and non-terminals. So y1 can be either a terminal or a non-terminal. Y2 can be similarly a terminal or a non-terminal. And similarly for yk, which is either a terminal or a non-terminal. So now if x is a non-terminal and we have a production, x produces y1, y2 up to yk, then first of y1 will be a part of first of x. The first of y1 will be in the first of x, because whatever the terminal symbol we are able to derive from y1, if y1 is a non-terminal. If y1 is a terminal, definitely it is itself a first of y1. But if y1 is a non-terminal, then whatever the first terminal symbol we are able to derive from the y1 will be in the first of x. So basically through the first of x, we are able to identify which is the correct alternative of the non-terminal x which is applicable. Now if y1 produces null, if we are able to derive null from y1, if there is a production or we are able to derive null from this y1, then the symbol which is in first of y2 will be in the first of x, because this y1 gives null. Because this y1 gives null, so whatever the first symbol which we are able to derive in the string will be the first symbol of y2. So that's why we have this rule that first of y2 will be in first of x if y1 derives null. Similarly, if y1 is deriving null, y2 is deriving a null, then there is a chance that in the derivation process, we are able to get the first of y3 as a first symbol from the derivation during x, because for y1 we'll put null, for y2 we can put null, and whatever is the first symbol in y3 that will derive from x. So this is how we'll continue up to all the symbols. So that's why if y of k minus 1 derives null, if y of k minus 1 derives null, then we'll place first of yk in also first of x. So whatever is in the last non-terminal symbol or terminal symbol, so first of yk will be placed in first of x. If y1, y2 up to yk minus 1, all symbols, not any one, I am talking about all symbols. If y1, y2 up to yk minus 1, if all symbols are deriving null, then we can put the element which is in first of yk in the first of x. So this is how we can construct the first set for any known terminal. So now let us see this with an example. So here you can see that for the first of a, here, you can see here first of a having two options, C and null. So you can see here first of a is nothing but we are getting first of C union, because we have two different alternatives, first of null. Now first of C, the first of C, so C itself is a terminal symbol, so we are getting the C, and first of null. So as per this rule number 2, we have this production, X produces null, from X we are producing null. So because of that, here we'll get C and null in the first of A. Similarly, for first of B, we have two different rules. So we can write like this, first of B is equal to, we have two things. So we'll write first of D union first of null. So this will give us D as well as null, because we have two different alternatives for this B. We have two different rules. Now when we consider first of S, so now for first of S, if we write, then for the first of S we can write as first of small a, capital B, and small b. So I can write like this, first of S is equal to first of small a, capital B, and small b. Now because this A is a terminal symbol, no need to consider the other symbols. So it contains only A. Because this is nothing but our y1. Now if y1 is deriving null, we have to think about y2. And if y1 and y2 both are deriving null, then we have to think about y3. And if y1, y2 and y3 all are deriving null, then we have to think about y4. But here in our case, y1 itself is A, which is not null. So we'll get only A in the first of S. So it is nothing but the first symbol which we are getting during the derivation from all these non-terminals. So now let us see more interesting examples on this, because this is a very complex concept. As you see more interesting examples, you will find that it is not very easy as it seems. So now informally, suppose we want to compute first of x1, x2, xn, then what we'll do, we'll write first of x1 plus first of x2 if null is a part of first of x1. So there is a similar thing which we have discussed, plus, so it is a union operation, first of x3, it is a union of all these sets, first of x3 if null is in first of x2. So this up to first of xn, if null is part of first of xn minus 1. So the most important thing is only add the null to first of x1, x2, xn if null is in first of x of I for all I. If null is derived from all these symbols x1, x2 and xn, from all of this, if all are deriving null, then and then null will be part of the first of x1, x2 up to xn. If any one symbol is deriving null or one or more symbol are deriving null, but not all, then you cannot put null in the first of x1, x2 up to xn. So now for first of x1, if we have another production, x1 gives z1, z2 up to zm, then we need to compute first of z1, z2, zm. Is it clear? What it tells that if x1 having its own production, like this, x1 produces z1, z2, zm, then first we have to find out first of z1, z2, zm. So that will be the first of x1. And once we are getting the first of x1, we can use that in this rule for first of x1, x2 up to xn. So let us see more interesting examples. So things will be clear to you. So now here let us see that how we can compute the first. So now here you can see for the first of E, it is straightforward. It is only B because we have only one rule. Now for first of S dash, we have two different rules. So we'll write first of ES union first of null. So now here you can see we have two different rules. We have two different rules. So from first of E, capital S, we are getting E because it is a terminal, and first of null. So we are getting null. So we have E and null from first of S dash. Now similarly, if I find first of S, where S is a non-terminal, we are getting the first of small I, capital E, T, S, S dash, union first of A. So now you can see in the first rule, we have I as a terminal. We have only I, which is a terminal symbol. So we'll write I, and for this we have A. So you're getting the answer is I and A. Because here this starts with a terminal symbol. And another alternative of S having only one terminal. So we are getting first of S, because if you start a derivation from S, either it will start with I or it will start with A. There is no another alternative. We have two different alternatives once you derive a string starting from S. Similarly, if I want to derive a string from S dash, we can use a small e. Or if we do not derive anything from S dash, we can use null. So because we have two different alternatives, we are getting like this. From S, either I can use this option in the top-down parsing, or I can use A. So now you can see the first symbol we are getting from S is either I, or first symbol which we are getting during the derivation is A. So this will help us to decide which is the right rule for us. So this will remove the backtracking. Basically, that is the main purpose of our predictive parser. We do not want to do any backtracking. Okay, now is this clear? First two examples. Any query in this? Yes, any query in this first two examples? So now for this example, can you tell what will be in the first of D? Can you tell what will be in the first of D? Yes, your answer. It is for the first of D. We have two things, D and null. It is D and null. It is the correct answer. Now similarly, if I consider a B, non-terminal B, for non-terminal B, can you tell what will be in the first of non-terminal B? It is definitely B and null. Yes. What will the answer? Can you tell? It is B and null. Now, first of A. What will be in the first of non-terminal A? So when you consider first of A, what you will get? It is nothing but first of A, which is equal to first of BD. Now you can see here, from B we are getting null. We have two options. First of B gives null because we have written this B and null both. So we are getting null from this. So what we have to write? First of B union first of D. The reason is because we are getting null from B. So now first of B will give us B and null because null is present, union first of D. D and null. Now null is a part of this two both. So we are getting first of A as B, D and null. So first of A will be having B, D and null. All three will be there. Because B is producing null. Because non-terminal B is giving null. If null is produced by the first symbol, then we have to consider the another symbol of the element. So that's why we are getting B, D and null. Now, from this, can you tell what will be in the first of S? Yes, can you share your answer for first of S? Yes, if you can share your answer for first of S. Okay, so it is, let us see. Because A is giving a null, because A is producing a null, we have to consider both. Because A is producing null, B, D and null, union A. Okay, now can you tell me what will the answer for first of S? The correct answer is A, B and D. Why null is not there? Because when you derive any symbol from S, you are never able to derive null. You are never able to derive null. From S we'll get AA. Now if I put null for this, still we are able to derive A. We are never able to derive null from S. Is it clear? So the correct answer is only A, B and D. null cannot be a part of first of S, because you are not able to derive null from S. Is it clear? Is this clear? Any query up to this? So now this is what you can see as the answer. First of D is D and null. First of B is B and null. First of A is B, D and E. And first of S is B, D and A. Null is not part of first of S. Now let us see one more interesting example. We have so many non-terminals here. The first of E, then first of E dash, first of T dash, and first of F. So now first we'll calculate first of F. Let us first consider the first of F. So first of F will give us opening parenthesis and ID. From this rule, we are getting opening parenthesis and ID. Both are terminal. We have opening parenthesis and ID from first of F. Now if I consider first of T dash, then first of T dash will give us, from the first one, we are getting the first of star F T dash union first of null. So this will give us star, which is a terminal. So we have to only consider that. And first of null. This first of null, because it's the production itself is null. So we are writing star and null for first of T dash. Similarly, if I want to find, then I can find for first of E dash. If I find for first of E dash, which is plus and null. It is plus and null. So that is what you can see here. That first of E dash, T dash and F. Now let us calculate first of T. So first of T will be first of F T dash. Now for F we have to check. Is it producing null? So our answer is no. F is not producing null. There is no null possible from F. So that's why first of F will be part of first of T. So we are getting opening parenthesis and ID in the first of T. That's why you can see first of T will be equal to first of F, which is equal to opening parenthesis and ID. Now let us see the most interesting one. First of E. So here you can see all the steps are given clearly for first of E. Let us see that for first of E we are writing first of T E dash. Now for first of T dash, it is first of T union first of E dash. But we don't have to consider first of E dash. We don't have to consider first of E dash because T does not produces null. Because T does not produces null. So we'll only consider first of T. Now for first of T, we are getting first of F union first of T dash. But we do not have to consider first of T dash because F does not produces null. So it is only first of F. And first of F will give us first of within parenthesis E union first of ID. So now this will give us opening parenthesis and ID. So I think now this is a very interesting example. This will help you to understand actually the concept of first with sufficient detail. Okay, now let us go through one more interesting example. Here, the first of B is given to us. The first of B is given to us. It is G and null. It is clear because we have direct option. For first of non-terminal C, we have H and null. We have H and null. So now using this, can you tell what will be in the first of A? What will be in the first of A? Can you tell? So what we can write for first of A? Yes, can you share your answer? Because this requires a lot of practice. So now first of DA. Now when you consider this first of DA, definitely DA and A both are terminals. So we have to write only this because when you derive, always derivation starts with D. Always the derivation starts with D. So first is always giving you one symbol, not more than one, which is the first symbol we are getting in the derivation. So this is equivalent to first of D. It is nothing but first of D. Union first of BC. So now union first of BC. So we have to write first of B union the first of C. The reason is from B we are getting null. From B we are getting null. B is giving null. So there is a chance that we will not use B in some derivation and we'll directly use the C. The derivation may be like this. From A we'll write like this B and C, and then we'll directly write C. We'll not use B. So because of that, first of A will be the first of C also. So now this will be your small d union first of B. So first of B is your G and null union first of C, H and null. So now if I combine all this, now what is the rule that if we are getting a null in all the productions, so now here from A we are getting DA, we are getting DA. So this is giving us D. Union, now B is giving null, C is also giving a null. B and C both are giving null. So here we'll write G, H and null. So here this is giving us D, this is giving us G, H and null. So finally what we'll get? The answer is D, G, H and null. So final answer will be D, G, H and null. That is the correct answer. So if we consider it is like this, we'll get this D, G, H and null. D, G, H and null. From first of DA we are getting D. Then from first of B we'll get G, null and null. Why we are subtracting null? Because if null is present in both, if null is present in both, then and then it will be a part of the final answer. So because B is giving null, C is also giving a null. So we are adding null in the list. This is why we are getting D, G, H and null in first of A. Now the most important thing, we want to find first of S. We want to find first of H. only few students are writing the answers. What about others? We have 80 students in the group. This needs a lot of practice. Because in top-down parsing, you have to find out the first set for every symbol. You have to find out a follow set for every symbol. If both of them are correct, then and then you are able to construct a top-down parsing table properly. Then and then you are able to construct a top-down parsing table properly. And you can do the top-down parsing. Otherwise, you cannot perform a top-down parsing. So normally weightage of first will be 3 marks or 4 marks. Then weightage of follow will be 3 and 4 marks. It will be a question of 12 marks. One question, 12 marks. So if you make any mistake in any one example, in any first calculation, it will totally make your entire example incorrect. So now let us see how to calculate this. So what I will do, I have to calculate first of A, B, C first. Then I have to calculate first of C, B, capital B. And I have to calculate first of capital BA. So now if I consider capital BA, then from first of B we'll get G and null. Because null is there, we'll consider, because this B is producing null, we have to also consider this. So if I eliminate null, because here null will be added if entire production is giving us null. So finally what we'll get from this G and A, from first of BA, we'll get G and A. Null will not be there because this A will be always there. So our answer will be from first of BA, it will be G and A only. So now can you tell what about CBB? The CBB. You should know first value of first of CBB. So now from this you can see first of C is H and null. The first of C is H and null. But B is present. Small b is present. So first of CBB will be only two values, H and B. Because non-terminal C gives us H and null, but we cannot consider null because this entire part, capital C, small b, capital B, does not derive null. So we are getting h and small b from first of CBB. Okay, then we have to calculate first of ABC. We have to calculate first of ABC. The first of ABC. So it depends on first of A. It depends on first of A. D, G, H null. Null is present. So we have to consider first of B. So it gives G, D, G, H null and null so far, and C. C is also giving us null. C is also giving us null. So it is giving us D, G, H null, all four. So it is D, G, H null for first of ABC. D, G, H and null. D, G, H null. We have four elements over here. So now using this, Now if I want to find first of S, we have to find first of S with this information with us. So now finally, if I consider, we have done all these steps. We have found out first of BA, it is G and A. Then first of C, capital C, small b, capital B, it is H and B. First of ABC, D, G, H null. Now we will find out first of S. So you can see from here, we have three different alternatives. First of ABC, here it is first of ABC, then first of capital C, small b, capital B, and then first of BA. So this will give us A, B, D, G, H null. This will give us A, B, D in this, because null is present in all the three. You can see here, null is a part of clear, null is a part of all this. Null is a part of first of ABC, it is a part of first of C, small b, capital B, it is also a part of first of BA. So because of that, null is present in all these three. Even though if it is present in any one, here we are considering three different alternatives. These are three different alternatives. So if any alternative is giving null, it will be a part of S. Fortunately here, null is a part of all the three alternatives. Null is a part of all the three alternatives. So no need to worry, because definitely it will be a part of first of S. It is a part of first of S. But even it is a part of only one alternative. Even though it is a part of only one alternative, we have to consider that. So now let us see one more interesting example to understand this process, because this is the main criteria for calculation of predictive parsing table. Now here the first of E non-terminal, then first of X, first of T, and first of Y we have to calculate. For terminal symbols it is straightforward. So now can you tell what will be in the first of Y? Yes, any query? Yes, any query? Okay, here from this we are eliminating this null, right? Because this first of BA is giving us GA. This is giving us GA, and this is giving us HB. This is giving us HB, right? This is giving us HB. Because this null is eliminated because of this first of small b, capital B. This null is eliminated because of first of small b, capital B. So we are writing HB as we have done in the previous slide also. Here there is a correction in this slide. Right? We have done in the same way. First of capital C, small b, capital B give us HB, because B is there as I have written. For first of BA it will be GA. So here there is a small correction in this slide. And here null is present here, so it will be a part of the first of S. So no change in the final answer. The final answer will be as it is. Okay, now we are here. We want to find first of y. We want to find first of y. It is star null. Yes, it is star and null. Because this y gives us star and this gives us null. So it is star and null. Now similarly, if I consider first of x, it is first of x. It is plus and null. Now it is interesting. First of t. Yes, first of t. Here keep in your mind that this int is a complete terminal. Int is a complete terminal. Don't consider it as only I. First of t, it will be int and opening parenthesis. From this, we are getting this int, which is a terminal. Why it is a terminal? Because it is not used as a non-terminal. And from this, we are getting opening parenthesis. So we have opening parenthesis and integer. Okay, now the most important one, first of e. Yes, what is the answer for first of e? Can you tell? So now if you look at this, first of e is nothing but first of t, because t is not producing null. So first of e is equal to first of tx, but here we'll get only first of t, as t is not giving null. So we are getting integer and opening parenthesis in the set. So I think it is clear now. Now let us see the very interesting example, which is really somewhat tough as compared to all this. This is what we have done so far. Let us consider this example. Let us find out the values for first of j. The first of non-terminal j in this. Yes, can you tell? What will answer for first of j? Is comma and null. Then first of, let us consider another one. First of I is id. Then first of y it is implements null. Is it visible to all? Is it visible? Okay. I think now it is visible. So it is implements and null. Yes. Then first of x. Yes, first of X will be this. Now let us consider the last one, the first of C. First of C. So now if I consider the last, we'll get this. The first of C will be public, final and class. It is public, final and class. So I hope now this calculation of first set is clear. The calculation of first set is now clear. So in this session, we have learned how to calculate the first set from the given grammar. Now in the next session, what we'll do is we'll calculate the follow set from the given grammar. This is a calculation of first set. Similar to that, we'll calculate a follow set from the different symbols of the grammar using another approach. And once we know the first and follow set, then we can calculate the predictive parsing table and we can derive any string. Yes. Okay. Now, can you tell me, have you faced any difficulty in the question paper? Any query in the question paper? Was it lengthy? Yes. Was it tough? Any suggestion related to question paper? You can share this view. Okay, so today we'll end the session here. Tomorrow we'll see how to calculate the follow set. So this next two lectures are also linked lectures. Don't miss any lecture, otherwise you are not able to solve the complete example of top-down parsing. All these lectures are linked. Next 2-3 lectures are linked with the same top-down predictive parsing table and how to construct the predictive parsing table. Thank you.